There is a place in the universe that doesn't behave the way space is supposed to. Not a black hole, not a neutron star, not a supernova remnant or a collapsing nebula, or any of the violent, luminous spectacles that space documentaries love to show you. This place is defined by the complete and total absence of all of those things. It has no stars, no planets, no galaxies, no dust clouds catching faint light from some distant source, no magnetic fields worth measuring, no gravitational anchor pulling anything anywhere. Scientists have a name for it, and the name they chose is almost insultingly plain, given what it actually is. They call it a void. But the specific one we're talking about, the one that sits roughly 700 million light years from the planet you're standing on right now, is something that challenges a much deeper assumption. The assumption that space, no matter how empty it looks, is always, on some level, full of something. This place suggests otherwise. And when you start to really sit with what that means, the unsettling part isn't the emptiness itself. It's what the emptiness implies about everything around it. Hold on to that, because we'll come back to it. Most people, when they think about deep space, imagine something like a vast ocean of black, with islands of light scattered through it. Stars here, galaxies there, nebulae glowing in the middle distance. The visual language of space exploration has given us this picture, and it's not wrong exactly, but it is radically incomplete. The reality of the universe's structure at its largest scales is far stranger than a scattered archipelago of stars. The universe is not distributed evenly, it is not random, and it is not simply dark between the bright spots. At scales that dwarf anything a human mind can genuinely process, the universe is organized into something that cosmologists describe, with some frustration, as a cosmic web. Filaments of matter, impossibly long strands of galaxies, and dark matter and gas stretch across hundreds of millions of light years, intersecting and connecting in a structure that, when mapped, looks disturbingly like the neural network of a living brain, or the lattice of a soap bubble, or the skeleton of something enormous that no one has ever named. And between those filaments, between the strands of the web, are the gaps, the voids. Regions of space where the gravitational pull of everything that exists has slowly, over billions of years, stolen the matter away and left almost nothing behind. The universe didn't create these voids by placing emptiness there. It created them by moving everything else somewhere else. That distinction matters more than it might seem right now. Remember it. The void we're examining, the one that has earned the informal title, the Great Nothing, is called the Boötes Void, named for the constellation that sits in the direction of it from Earth. You can locate it yourself. On a clear night, find the Big Dipper. Follow the arc of its handle outward until you reach a bright, distinctly orange star. That's Arcturus, the fourth brightest star in the night sky, a red giant about 37 light years away. Now, between the Big Dipper and Arcturus, in that stretch of northern sky that looks unremarkable in every way, you are looking directly into the void. 700 million light years away, invisible to the naked eye, sitting there in the direction your finger points. It's been there longer than complex life has existed on Earth. And until 1981, no one knew it was there at all. The discovery wasn't dramatic. It didn't come from a single telescopic image or a chance observation by one brilliant astronomer who noticed something wrong. It came from a survey, a painstaking, systematic attempt to build a three-dimensional map of the universe by measuring the redshift of galaxies, a method that uses the stretching of light to determine not just where something is, but how fast it's moving away from us, which in an expanding universe translates directly to distance. Astronomers Robert Kirshner, Augustus Oehmler, Paul Schechter, and Stephen Schechtman were conducting one of these surveys in the late 1970s and early 1980s, cataloguing galaxies across a region of sky in the Boötes constellation, and what they found in the data was not a region sparsely populated with galaxies. It was a region almost entirely absent of them. Where the survey predicted galaxies based on the uniform distribution model that most cosmologists assumed at the time, there were none. A spherical gulf, roughly 330 million light-years across, containing, by all observable measures, almost nothing. The initial paper describing the discovery used carefully measured scientific language, but even in that restraint, the implication was clear: the universe contained a hole. A real, physical hole in the structure of the cosmos. Not a region slightly less dense than its surroundings. A region that, at the scale of an entire survey field, simply registered as absent. This is where things stop making sense in the way you were probably expecting them to. Because the instinctive response to learning about an enormous void in space is to assume it must be somehow unusual, an anomaly, a fluke, an artifact of young universe physics that produced one strange region and left the rest of space well populated and normal. That instinct is wrong, and the degree to which it's wrong is one of the quieter, more destabilizing facts in modern cosmology. Voids are not the exception in the structure of the universe. They are, in terms of volume, the rule. Current estimates suggest that cosmic voids regions of space significantly less dense than the average make up approximately 80% of the total volume of the observable universe. 80%. The matter that makes up everything, every galaxy, every star, every planet, every atom of gas, every particle of dark matter, is compressed into roughly 20% of the available space. The filaments of the cosmic web, as vast as they are, as numerous as their galaxies, are the thin walls of an enormous foam, and the foam is mostly air. This becomes important later, because it reframes the question of the Boötes Void entirely. The Boötes Void is not strange because voids exist. Voids are everywhere. The Boötes Void is strange because of how large it is, and because, for a long time, its size didn't fit the models. When astronomers first measured its diameter at roughly 330 million light-years, that number was deeply uncomfortable. The standard cosmological models of the time models, built on our best understanding of how gravity assembles matter over time, how long the universe has existed, and how fast structure formation proceeds, predicted that a void of that size simply shouldn't exist. Not yet. The universe hasn't had enough time. The process by which gravity slowly evacuates these regions, pulling matter into the surrounding filaments and leaving the voids increasingly empty, is real and measurable and well understood. But it operates on enormous timescales. And the Boötes Void appeared, to the cosmologists studying it in the early 1980s, too large to have formed naturally in the 13.8 billion years the universe has been expanding. This triggered a quiet debate that persisted for years. Some researchers proposed that the void was real, but that our measurements were contaminated, that there were galaxies in there. We were missing, too faint or too distant to appear in the survey. Some proposed that the void was the result of an enormous void collision, multiple smaller voids that had merged over time into one superstructure. Some proposed explanations involving topology, the idea that the universe might have a more complex geometric shape than a simple infinite expansion, creating apparent gaps in galaxy distribution that don't reflect true emptiness. And some proposed, in the way that scientists occasionally propose things they can't quite say out loud, that there might be something about the Boötes Void that the standard model of cosmology doesn't fully account for. None of these explanations were settled quickly, and the question of whether the Boötes Void is genuinely anomalous, or whether it's a natural, if extreme, product of normal cosmic structure formation is a question that cosmologists are still, to varying degrees, debating. The current consensus leans toward natural formation. The mechanism is gravity, the timescale is extreme, the void is real. But the consensus is not unanimous, and there are researchers who still look at the numbers and feel that something about the Boötes Void is not fully explained by the models we have. Remember this, because the implications of the void being anomalous of it, being something that structure formation alone cannot account for led somewhere that most cosmological discussions don't go. But we'll get there. For now, let's do something that the science of voids rarely invites people to do. Let's actually go there, not metaphorically, not with a quick mention of how many light years away it is followed by a pivot to something visual and dramatic. Let's follow the actual journey with the actual numbers, and let the actual scale of what you would experience press against your understanding of distance and time until something gives. You leave Earth. The departure itself is already a problem that most science communication glosses over. Leaving the surface of a planet is not the same as leaving its gravitational influence. Earth's gravity extends outward in a gradient that only approaches zero asymptotically. It never actually reaches it, but at a certain distance it becomes negligible compared to other forces. The moon's gravity, the sun's gravity, these become dominant at different thresholds. To leave the solar system entirely, you don't simply accelerate outward. The sun's gravity governs the orbital dynamics of every object in the system out to enormous distances. The Oort cloud, the theoretical reservoir of long-period comets, extends possibly a quarter of the way to the nearest star. Breaking free of solar gravity requires reaching a speed called solar escape velocity, which at Earth's orbital distance is about 42 kilometers per second. For context, Earth itself moves through its orbit at roughly 30 kilometers per second. Your spacecraft needs to exceed solar escape velocity relative to the Sun, while also managing its trajectory relative to Earth's orbital motion. This is not impossible, but it is the kind of problem that forces you to leave in a spiral rather than a straight line, making progressively wider orbits until you've built enough velocity to stop orbiting entirely and simply leave. The fastest spacecraft ever launched by human beings, the Parker Solar Probe, which uses repeated close approaches to the Sun to slingshot itself to extraordinary speeds, reaches approximately 550,000 kilometers per hour at its fastest. This is roughly 0.05% of the speed of light. It is, by any human standard, astonishing. It is also, by interstellar and intergalactic standards, effectively motionless. At that speed, reaching the Boötes Void 700 million light-years away would require approximately 1.3 trillion years. The current age of the universe is 13.8 billion years. You would need about 94 times the current age of the universe just to arrive. But you have a faster ship. You have, in this thought experiment, a ship that can travel at some meaningful fraction of the speed of light. Let's say, for simplicity, that you can travel at light speed itself, which is physically impossible for any object with mass, but useful as a reference point. At the speed of light, leaving the Milky Way galaxy alone would take 26,000 years, assuming you happen to be moving directly toward its edge. You are not at the edge. You are roughly halfway between the galactic center and the outer rim. The Milky Way is 100,000 light years across, and Earth sits about 26,000 light years from the center. So your shortest path to the galactic edge is roughly 24,000 light years. 24,000 years at the speed of light. And that's just the first galaxy, the one you already live in. After leaving the Milky Way, the sky changes. This is something worth pausing on because it is genuinely disorienting when you follow it carefully. From inside the Milky Way, the sky, when you look outward from the disk, is populated by hundreds of millions of individual stars visible to the naked eye, and on a clear night, by the diffuse glow of the galactic plane itself. But the moment you cross the outer edge of the galaxy and enter intergalactic space, all of that disappears. The individual stars become invisible. What remains are distant galaxies, faint smears of light, most of them requiring powerful instruments to detect. And as you travel outward, farther from the local group of galaxies that includes the Milky Way and Andromeda, even those faint smears become dimmer, fewer, and finally, as you approach the edge of the void, they cease entirely. There is a precise moment in this journey, not a dramatic one, not marked by any sound or sensation, but a precise one where the last galaxy falls below the threshold of visibility even with the naked eye. Where you cross from a universe that, however faint, offers some reference of light into a universe that offers none. The transition happens at the boundary of the Boötes Void, and after that boundary, in every direction, for 330 million light years, there is nothing your eyes can resolve as a light source. The cosmic background radiation exists, technically the faint afterglow of the Big Bang that permeates all of space uniformly, but it is microwave radiation, invisible to human eyes, and it is everywhere equally, offering no directionality, no reference, no sense of position or motion. You are in the dark, not the dark of a room with the lights off, where there is still the warmth of familiar surroundings and the knowledge of where the door is. Not the dark of a cave, where the absence of light is total, but the walls are close and solid. The dark of the Boötes Void is a dark that has no walls, in every direction, for distances that dwarf the entire span of human civilization's imagination. There is nothing to see. The temperature of the space around you is approximately 2.7 degrees Kelvin, just above absolute zero, which is the ambient temperature of the universe maintained by that same cosmic background, radiation. The thermal environment is as inhospitable as physics allows, without the dramatic violence of a stellar body nearby. Coldness this profound is not dramatic. It doesn't roar or burn. It is simply the absence of energy, the resting state of matter with nowhere further to fall. And if you slipped out of your spacecraft at this point, if some accident or decision placed you in your suit, floating in the center of this void, you would experience something that has no analogue in any human experience, and no adequate description in any human language. You would be falling, in a sense. Microgravity means there is no up or down, no orientation, no direction that pulls you more than any other. But unlike the falling you experience in an aircraft or in freefall, there would be no reference against which to measure your motion, no ground rushing up, no horizon staying fixed. no stars moving relative to each other to indicate your trajectory. In the center of the Boötes Void, with no visible light source in any direction, you would be unable to determine whether you are moving or stationary, whether you are spinning or still, whether minutes are passing or hours. The human vestibular system, which generates a sense of balance and orientation from gravitational cues and the rotation of fluid in the inner ear, would still function. You would feel the slight inertial signals of any rotation or acceleration your body underwent. But there would be no external confirmation, no way to verify whether what your inner ear reports matches any objective reality. This is the part that most descriptions of the void skip over, because it's not about the physics, it's about perception. Human consciousness is built in a very fundamental way on contrast. We perceive light because there is dark. We perceive sound because there is silence. We perceive motion because there is stillness against which to measure it. We perceive ourselves as existing in a particular location because that location has features, landmarks, gradients, references that distinguish it from other locations. In the center of the Boötes Void, all of those contrasts collapse. The dark is not contrasted against anything bright. The silence is absolute. The stillness or the motion, you can't tell, has nothing to define it. And in that environment, the human sense of self-location, of being a body in a particular place at a particular time, begins to deteriorate in ways that are not metaphorical but neurological. Sensory deprivation studies conducted on Earth float tanks, isolation chambers, environments carefully engineered to reduce external stimuli, produce measurable changes in consciousness within hours. Mild hallucinations, distortion of time perception, heightened sensitivity to internal signals, heartbeat, breathing, the subtle crackling of joints. Extended sensory deprivation produces more severe effects. The brain, starved of external input, begins generating its own. The experience is not peaceful, at least not for long. It is, in many subjects, deeply distressing, because the brain is not designed to operate without input. It is designed to model a world, and when the world provides no data, the model begins to run on itself. Now extend that deprivation, not for hours, but for the time it would take you to cross the void, or simply to drift within it. Extend it for the indefinite future of a body in microgravity, with no propulsion and no signal. And consider what it means for a consciousness, whatever consciousness is, whatever it requires to exist in an environment that offers it absolutely nothing to work with. This is where the void stops being a physics problem and becomes something else. Something that the instruments of science can describe in numbers 330 million light-years, 2.7 degrees Kelvin, approximately 60 galaxies, but cannot fully account for. Because those numbers describe the void from the outside, from a position that has references and can make comparisons. From the inside, in the absence of any reference, those numbers become meaningless. The scale of the void is not something you can experience. It is only something you can be lost in. There's a question that doesn't get asked often enough in conversations about the large-scale structure of the universe. Not the question of what voids are, or how they form, or how large they can get. Those questions have reasonably well-developed answers. The question that gets skipped is this: why does the cosmic web exist in the form that it does? Not what forces created it. Gravity is the obvious answer, and it's correct. But why does gravity, acting over the lifetime of the universe, produce this specific architecture. Filaments and nodes and voids, rather than, say, a more uniform distribution of matter, a sphere of dense clusters at the center with decreasing density outward, some other geometry entirely. The answer to that question reaches back to a moment so early in the universe's history that the physics describing it are still being refined, and it connects the enormous emptiness of the Boötes Void to something that happened in the first fractions of a second after the Big Bang. And once you see that connection, the void stops being a passive absence and starts looking like evidence of something. In the very early universe, within the first tiny fractions of a second after the initial expansion began, the cosmos was a hot, dense plasma in which matter and energy were so thoroughly mixed that the concepts we use to distinguish them barely apply. Particles were constantly created and annihilated. Photons and matter were coupled together in a single fluid, and within this fluid there were fluctuations, tiny variations in density, so small that they would have been indistinguishable from thermal noise to any hypothetical observer, but real differences in the concentration of matter and energy from one point to another, distributed across the volume of the early universe in a specific statistical pattern. These fluctuations are called quantum fluctuations, and their origin lies in the mechanics of quantum fields, the same framework of physics that governs the behavior of subatomic particles and the probabilistic nature of measurement at small scales. The universe, in its first moments, was quantum mechanical at every scale. And quantum mechanics is inherently probabilistic. It does not produce perfect uniformity, it produces variation, structured, mathematically describable variation, but variation nonetheless. Those fluctuations, those infinitesimally small differences in density from one region to another, in the first fractions of a second of the universe, are the direct ancestors of the cosmic web. Gravity amplified them. Over hundreds of millions of years, and then billions, the regions that were slightly denser attracted more matter. The regions that were slightly less dense lost matter to their neighbours. The process compounded. Dense regions became denser. Empty regions became emptier. The filaments grew along the axes where matter accumulated fastest. The voids expanded into the spaces where matter departed most completely. The architecture of the present-day universe, every galaxy, every cluster, every filament, every void, including the Boötes Void, is a gravitationally amplified imprint of quantum fluctuations that occurred before the universe was 1 second old. This is the part most people miss. The Boötes Void is not an accident. It is not a random gap that happened to grow large because of some local quirk of initial conditions. It is the product of a process that began at the quantum scale and operated for nearly 14 billion years to produce a structure 330 million light years across. The emptiness of the void is not the absence of a process, it is the result of one. Every cubic light year of that void represents matter that was pulled away by the gravity of the surrounding filaments, redistributed into the walls and nodes of the cosmic web, leaving the interior progressively more depleted over geological timescales so vast that human intuition cannot follow the math to its conclusion. The void is not where nothing happened. It is where something happened completely. The evacuation is total. The process ran to its conclusion. And here is where the question of anomaly reappears. Because if the Boötes Void is simply the largest natural void produced by normal structure formation operating on normal initial conditions over the normal age of the universe, then it should be explainable by the standard cosmological model, the lambda CDM model, which describes a universe composed of ordinary matter, dark energy, and expanding according to well-established equations, and in broad strokes it is. The mechanisms are understood. The physics is not in dispute, but the size of the Boötes Void has, since its discovery, sat at an uncomfortable edge of what those models predict should be possible, not outside the predictions entirely, not definitively anomalous in a way that demands a new theory, but at the margin, at the place where the standard model produces its rarest expected outcomes, and where the distinction between extremely rare natural event and something the model doesn't fully account for becomes genuinely difficult to draw. Some researchers have proposed that the Boötes Void may be a supervoid, not a single coherent void, but the result of multiple adjacent voids merging as their boundaries expanded over time. This would make the 330 million light-year figure less surprising, because it would represent not one void's growth, but the combined growth of several, which eventually became indistinguishable. This is a plausible mechanism, and it brings the Boötes Void's size into better agreement with standard model predictions. But it also makes the void harder to characterize precisely, because supervoid boundaries are more complex than single void boundaries, and the internal structure, the approximately 60 galaxies observed within the void, could reflect the remnant filaments of the original separate voids rather than the true interior of one continuous empty region. The 60 galaxies deserve attention because they are one of the most quietly strange details of the Boötes Void's profile. 60 galaxies in 330 million light-years of space sounds like it might be enough to break the sense of true emptiness. It isn't. To understand why, consider the scale. The observable universe contains an estimated 2 trillion galaxies. The Boötes Void contains approximately 60. If you were to distribute 2 trillion galaxies uniformly across the observable universe's volume, and then carve out a region the size of the Boötes Void, that region would be expected to contain something on the order of 10,000 galaxies at minimum, and likely far more. 60 is not 10,000. 60 is not even 1,000th of 10,000. The Boötes Void, even accounting for the 60 galaxies within it, is almost incomprehensibly underdense relative to the cosmic average. And those 60 galaxies are not distributed evenly within the void. They are grouped clustered in a single filament that stretches roughly through the void's interior, which means that the majority of the void's volume contains not 60 galaxies, but effectively 0. The filament of 60 occupies a thin strand in a volume that, if scaled to the size of the Earth's orbit around the Sun, would make that filament thinner than a human hair. The rest is empty. Genuinely, measurably, almost completely empty. If you were placed at a random point within the Boötes Void, not at the filament, but at a random point in the total volume the nearest galaxy to you would be, on average, more than 10 million light-years away. At the speed of light, 10 million years away, and it would not be visible to the naked eye at that distance. Even a large luminous galaxy like the Milky Way, at 10 million light-years, would appear as a point of light roughly equivalent to the faintest stars visible from Earth under perfect conditions, and only under perfect conditions, which are irrelevant in a void where you are the only observer and there are no conditions to speak of except the absolute darkness of intergalactic space. For all practical purposes, of unassisted human perception, you would see nothing in every direction, without exception. Now here's the part that requires a mental shift. The darkness of the Boötes Void is not the darkness of night. This distinction sounds obvious, but it cuts much deeper than it appears to. On Earth, nighttime darkness is a local, temporary condition produced by the geometry of a rotating planet blocking a single star's light. The stars are still there. The sun is still there. The Milky Way is still there. The darkness of night is a shadow, and shadows have edges. In the void, the darkness has no edges. It is not a shadow cast by anything. It is the baseline state of the region, the default condition that nothing is bright enough to interrupt. The difference between nighttime darkness on Earth and void darkness is the difference between being in a temporarily unlit room in a building full of people and being in a region of space where the nearest building is 10 million light years away, and you have no way to travel there. Human beings have spent enormous effort creating light. Fire, candles, gas lamps, electric bulbs, LEDs, laser arrays, stadium floodlights, cities visible from orbit, navigation beacons visible from hundreds of kilometers. The entire project of artificial illumination is, at some level, a response to the existential discomfort of darkness. We don't like it. We have a deep, probably ancient aversion to environments where we cannot see, and we have invested enormous resources across the entire span of recorded history in defeating that condition wherever we encounter it. The void makes all of that effort irrelevant. Not inadequate irrelevant. A flashlight in the Boötes Void would illuminate the space immediately around you. It would not, in any meaningful sense, change the darkness of the void. The void's darkness is not a deficit of light that can be locally corrected. It is the condition of a volume 330 million light-years across, in which the generation of light is insufficient to escape the region's fundamental emptiness. Hold on to that thought, because it connects to something much larger. The rate at which stars form in any given region of space depends on the presence of raw material gas clouds, molecular hydrogen, the diffuse plasma that exists between stars in a galaxy. Star formation is a process that requires density. You need enough matter concentrated in one place for gravity to compress it to the temperature and pressure at which nuclear fusion ignites. In the cosmic web's dense filaments and cluster nodes, star formation proceeds actively, driven by the ongoing accretion of matter and the dynamics of galactic interaction. In the voids, the situation is almost precisely the opposite. Matter is scarce. Gas clouds are absent or too diffuse to collapse. The few galaxies that exist within voids tend to be smaller, older, less active than their counterparts in dense environments. They are not forming many new stars. They are, in a sense, running out of fuel without the possibility of resupply. The Boötes Void is not a place where new stars are being born. It is not a place where planetary systems are being assembled. The chemical conditions for complex chemistry, the heavier elements produced by stellar nucleosynthesis, the supernovae that distribute those elements into the interstellar medium, the subsequent generations of stars that incorporate those elements into their formation and into the planets that form around them. Those conditions require active, generative, stellar environments. The void's 60 galaxies are relics, not nurseries. They are isolated, slowly evolving, running down on timescales so long that the word slowly doesn't capture it. In the void, the universe is not actively building. It is passively aging. This matters in a way that extends beyond the physics of star formation. Because if the void is a region where the generative processes of the universe have essentially stopped, where there is no new stellar material, no new chemistry, no ongoing assembly of complex structures, then it is a region where time behaves differently in a non-relativistic sense. Not differently according to the equations of general relativity, where the curvature of space-time near massive objects causes measurable time dilation. Differently in a more fundamental, if less mathematically precise sense, a region where the arrow of time, the thermodynamic gradient that runs from order to disorder, from low entropy to high entropy, has almost nowhere further to go. The void is already near its endpoint. It has already completed the process of emptying out. What remains is only the slow, continuing expansion of space itself, pulling the void's boundaries slightly wider, year by year, at a rate that no human observation could detect directly. The universe, at its largest scales, is heading somewhere. The expansion that began with the Big Bang has not stopped, and the current evidence, particularly the discovery of dark energy in the late 1990s, suggests that it is not merely continuing, but accelerating. Space itself is stretching. The distances between galaxies that are not gravitationally bound to each other are growing, and growing faster than they were 1 billion years ago, and faster than they will appear to be growing 1 billion years from now. In the very far future, on timescales measured in tens of billions and eventually trillions of years, this acceleration will have a specific effect on the cosmic web. The filaments will not dissolve. Gravity is strong enough, locally, to hold galaxies and clusters together against the expansion. But the voids will grow. The empty regions of space will become larger. The galaxies in the voids surrounding filaments will appear to recede further and further from any hypothetical observer within the void. Eventually, in the most distant reaches of cosmological time, the recession speed of those galaxies will exceed the speed of light, not because they are moving faster than light, but because the space between them and the observer is expanding faster than light can cross it. At that point, the galaxies on the void's boundary will simply disappear. Not because they cease to exist, but because the light they emit can no longer reach across the expanding void to be observed. The Boötes Void, in the far future, will become more isolated, more complete, more absolute in its emptiness. The 60 galaxies within it will continue their slow decline. The boundary galaxies will become unreachable. The void will not grow violent or dramatic. It will simply grow quieter. And eventually, on timescales that make the current age of the universe seem like a brief opening act, the void will be something that has no name in any language that currently exists, because no mind capable of naming it will have access to it. This is not speculation. It is the direct implication of the physics we currently understand, applied to a region of space that is already, by any human measure, incomprehensibly empty and incomprehensibly large. The Boötes Void is not what the universe will look like everywhere in the far future. It is what the universe will look like everywhere in the far future once the local structures, the filaments, the clusters, the galaxies, have had time to lose their connections to each other. The void is not the universe's past. It is a preview of the universe's future, a region where the final state of cosmic structure has already, in large part, been achieved. And it has been sitting there 700 million light years away, visible in principle from Earth for as long as Earth has existed, waiting to be recognized for what it is. Here's the part that most cosmological discussions stop before reaching. If the void is a preview of the universe's thermal and structural future, a region where complexity has been maximally reduced, where generative processes have effectively ceased, where the conditions for life, chemistry, and observation are essentially absent, then it raises a question about observation itself, about what it means for something to be known. The Boötes Void has been observed by human astronomers using telescopes on a planet in a galaxy on the edge of a filament of the cosmic web. The observation is possible because the observer is outside the void, in a region dense enough with stars and planets and complex chemistry to produce beings capable of building telescopes and interpreting data. The void cannot observe itself. It contains no instruments. It contains no observers. It contains, with whatever charity we extend to the 60 galaxies within it, effectively nothing capable of turning its attention outward and registering its own existence. This is a strange property for a thing to have. Most of the objects we study in science exist independently of our observation of them. Stars burn, whether or not anyone is watching. Planets orbit, whether or not anyone has mapped their trajectories. Black holes consume matter, whether or not anyone has detected their gravitational signatures. But the void, in a sense that goes beyond metaphor, only becomes a void in the context of observation from outside. Its emptiness is not a property it possesses in isolation. It is a relationship between the void and the surrounding structure. The void is empty because the surrounding filaments are full. The surrounding filaments are full because gravity pulled matter toward them. The matter moved because the initial quantum fluctuations set up a density gradient. The density gradient exists because the universe's earliest moments were quantum mechanical and therefore inherently variable. The void and the web are not separate features of the universe. They are complementary aspects of a single process, each defined by the existence of the other, which means that the Boötes Void, that 330 million light-year expanse of near absolute nothing, is not separate from the universe that contains it. It is not a hole in the universe, as some early descriptions of it suggested. It is the universe expressing one of its most fundamental tendencies at a scale large enough to see clearly. The tendency to differentiate, to move from uniformity to structure, to create concentrations and depletions, to organize matter into patterns that look, from a sufficient distance, like a web or a foam or a nervous system, and to leave behind, in the spaces between the concentrations, something that looks like absence, but is actually the record of everything that moved away. The void is not where the universe isn't. The void is where the universe has been. And this reframes the question we started with, the question of what it would actually be like to fall into the Boötes Void in a way that the physics alone cannot resolve. Because the question is not just about temperature or pressure or the visibility of distant galaxies. The question is about what happens to an observer, to a consciousness, to a mind with its particular dependence on reference and contrast and the presence of something against which to measure itself when it is placed in a region where the universe has completed its work, where the processes that generate complexity have run to their conclusion, where the only remaining dynamic is the slow expansion of space itself, imperceptibly widening the already vast distances between the void's sparse contents. The answer, to the extent that there is one, is not comfortable, and it is not finished. Because there is something about the Boötes Void that the cosmological discussion almost always overlooks. Not the physics of its formation, which is reasonably well understood, not the question of its anomalous size, which is actively debated, but the question of what the void's existence means for the distribution of possible observers in the universe, for the relationship between structure and the capacity for experience, for the question which sits at the boundary between cosmology and philosophy, and which neither discipline has fully claimed, of whether the architecture of the universe is, in some sense, structured in a way that concentrates the possibility of observation in the same regions where it concentrates matter. The cosmic web is not uniform, it is lumpy, it is structured, and the observers, the beings, capable of building telescopes and writing equations and asking questions about voids, are not distributed uniformly across the universe's volume. They are concentrated in the dense regions, in the filaments and the cluster nodes, in the galaxies where stars form and planets assemble, and chemistry runs long enough and complex enough to produce minds. The voids are not where observers live. Observers, by the logic of their own existence, must live in environments capable of producing them, and void environments are not, by any current measure, capable of producing them. This means that there is a region of the universe, a region that constitutes, by volume, the majority of the universe that has never been and will never be observed from the inside. The cosmic web contains observers looking outward. The voids contain no one looking at anything. The universe, as it exists, is self-observing in a radically non-uniform way. The dense regions see the empty regions from the outside. The empty regions see nothing at all. Whether this matters, whether a universe is in some sense incomplete without internal observers, or whether the concept of observation is simply irrelevant to regions that contain no observers, is not a question that physics can answer. It is a question that sits at the edge of what physics can even properly formulate, but it is a question that the Boötes Void makes unavoidable. Because the void is large enough and empty enough, and the physics of its future isolation are clear enough, that the question of what it is like in there really like, not in terms of temperature and galaxy counts, but in terms of what presence in that volume would mean for a mind, is a question that cannot be deflected by pointing to equations. There is no one in the Boötes Void to ask. And that fact, unremarkable as it seems at first, obvious as it sounds, when stated plainly carries implications that extend far beyond the void itself. Because if the universe's architecture systematically concentrates observers in the dense regions and leaves the voids observer-free, then the picture of the universe that observers have built, the maps, the models, the standard cosmological model with its precise parameters, is a picture built entirely from the perspective of beings who live in the unusual, overdense minority of the universe's volume. The 80% of the universe that is void is not represented in the data by observers within it. It is observed from outside, from the same dense filaments that created it by pulling matter away. The universe's self-knowledge, such as it is structurally biased toward the regions where complexity exists and away from the regions where it doesn't. This is not a claim that our cosmological models are wrong. The data is collected carefully, and the methods of inferring void properties from external observation are well validated. But it is a reminder that the perspective from which we observe the universe is not a neutral view from nowhere perspective. It is the perspective of beings who live in galaxies, in solar systems, on planets, in a specific and highly improbable region of a cosmos that is, in the vast majority of its volume, empty. Our understanding of emptiness is built from outside the emptiness. Our intuitions about what nothing looks like are the intuitions of beings surrounded by something. The Boötes Void, then, is not just a large structure in the universe. It is a kind of mirror, not a reflective one. There is nothing in the void to reflect anything, but a conceptual mirror, a region whose properties, when examined carefully, reveal something about the nature of the perspective from which it is being examined. To look at the void is to be reminded that you are looking from somewhere, that the somewhere you are looking from this planet, this solar system, this galaxy, this dense knot of the cosmic web, is not the default condition of the universe. It is the exception. The void is the rule, and the exception only knows it is an exception because it has, by some sequence of unlikely physical events, become capable of looking outward and noticing the difference. That is a strange loop, and it doesn't close cleanly, because the moment you follow it to its end, you arrive at a question that the loop itself cannot answer. If the universe's majority volume is empty, and if the observers are all in the minority volume, then the universe's self-observation is incomplete in a way that may be permanent and structural, not merely provisional. There may be properties of the void dynamics, phenomena, conditions that can only be known from the inside, and that external observation, however sophisticated, cannot fully recover. Properties that are, in principle, inaccessible to any mind that could exist to ask about them. This is where the physics ends and something else begins. And that something else is not mysticism or speculation in the pejorative sense. It is a genuine limit, a boundary of knowability that the structure of the universe itself imposes on the beings it has produced. The void does not hide its secrets deliberately. It has no intention and no concealment. But the fact of its emptiness, combined with the fact that observers require non-emptiness to exist, creates a situation in which the void's interior is, in a deep and possibly irresolvable sense, forever outside the reach of experience. You can map it from outside. You can measure its temperature, estimate its galaxy count, model its formation history, predict its future evolution, but you cannot be in it and know it. And you cannot know it and be in it. The two conditions are mutually exclusive in a way that goes beyond the practical impossibility of getting there. This becomes important, and we haven't reached the end of it yet. There is a concept in cosmology called the observable universe. Not the universe, the observable universe. The distinction is precise and it matters. The universe, in its totality, may be infinite. Current models do not rule out an infinite spatial extent, and some interpretations of inflationary cosmology actively predict it. But the observable universe, the region from which light has had time to reach us in the 13.8 billion years since the Big Bang, has a finite radius, approximately 46 billion light-years in every direction, producing a sphere of roughly 93 billion light-years in diameter. Everything within that sphere is, in principle, observable. Everything outside it is not because it doesn't exist, but because the light from those regions has not yet arrived, and in an accelerating universe, for the most distant regions, it never will. The expansion of space will outpace the light before it crosses the gap. This boundary, the cosmological horizon, is not a wall. It is not a place where the universe ends or where space has an edge. It is the limit of what any observer at our location can, even in principle, receive information about, and it moves. As time passes, light from slightly more distant regions arrives, and the observable universe grows. But in an accelerating expansion, the growth of the observable universe is slowing down. The acceleration of the expansion is pushing new regions beyond the horizon faster than the passage of time allows their light to reach us. Eventually, in the very far future, the observable universe from Earth's location, or whatever replaces Earth's location as an observational platform, will begin to shrink. The galaxies currently on the edge of our observational reach will cross the horizon and become permanently inaccessible. The universe will become, from any fixed vantage point, progressively smaller in terms of what can be known, even as it continues to expand in terms of absolute size. The Boötes Void is well within our current observable universe. At 700 million light-years, it is less than 2% of the distance to the cosmological horizon. We can see it, we can measure it, we can model it, but the void itself sits inside a larger context, the context of a universe that is actively working to reduce the observational reach of any fixed point within it. The void is not moving toward our horizon, but the logic that applies to the void's future isolation, the recession of boundary galaxies beyond communicability, is the same logic that applies to the universe as a whole over sufficient time. The void is a local, already advanced instance of a process that is universal and ongoing. Hold that thought, because it connects to something that most discussions of cosmic structure never reach. The question of what the universe is doing, not in the sense of what physical processes are occurring, but in the sense of what the net direction of all those processes adds up to, is a question that has a surprisingly clear answer at the largest scales. The universe is differentiating. It began in a state of near-perfect uniformity, hot and dense and smooth, with only those quantum fluctuations to break the symmetry. And it has been, for nearly 14 billion years, converting that uniformity into structure, concentrations and voids, dense filaments and empty expanses, complex chemistry in the overdense regions and bare vacuum in the underdense ones. The arrow of thermodynamic time points from uniformity toward differentiation, and the universe has been following that arrow consistently since the moment it began. But differentiation has a limit. You cannot differentiate indefinitely in a finite system without eventually reaching a state where the differentiation is complete, where everything that can be separated has been separated, everything that can be concentrated has been concentrated, and the system has reached its maximum internal variation. In cosmology, this endpoint has a name. It is called the heat death of the universe, or, more precisely, thermodynamic equilibrium at maximum entropy, the state in which no further thermodynamic work can be done, because there are no remaining gradients, no temperature differences, no density differences, no pressure differences for processes to operate across. A perfectly smooth, perfectly cold, perfectly inert expanse in which nothing happens because there is nothing left for anything to happen between. The cosmic voids are not the heat death. They are not the end point, but they are the leading edge of it. They are the regions of the universe that have progressed furthest along the path toward that final state. The dense filaments are still running hot, still forming stars, still producing the gradients that drive chemistry and complexity, and, in at least one known case, conscious observation. But the voids have already evacuated their gradients. They have already achieved something close to the maximum entropy available to a region of space that contains almost no matter. They are, relative to the active regions of the cosmic web, already near their end. This is not a comfortable thought, and it is not meant to be, but it is an accurate one, and accuracy, in this case, is more useful than comfort, because the implication of the void being a preview of the universe's endpoint is not simply that the future will be empty. It is that the present is already, in its majority volume, almost indistinguishable from that future. The 80% of the universe that is void is not waiting to become empty. It is already empty. The transition to a universe where complexity is impossible has not happened yet in the dense regions. But it has, for all practical purposes, already happened in the voids. The universe that astronomers describe as young and active and generative is, by volume, mostly a universe that has already settled. The activity, the star formation, the galaxy evolution, the chemistry is happening in a minority of the total space. The majority is already dark. Now here is the shift that changes the frame entirely. We tend to think of the universe as something that exists around us, a container, a stage, the place where things happen. And from inside a galaxy, inside a solar system, on a planet with an atmosphere and a biosphere and a civilization, that framing feels natural. The universe is out there, and we are in here, embedded in it, looking outward. The void challenges that framing in a specific way, because from the perspective of the void, if the void had a perspective, which it doesn't, but follow the logic, the situation looks different. From inside a region that constitutes 80% of the universe's volume, the dense, active, complexity-generating regions of the cosmic web would appear as distant, thin structures on the far horizon, narrow filaments of light in an otherwise dark expanse, not the dominant feature of the universe, but a marginal one. Thin walls of activity at the edges of a vast, settled darkness. From the void's hypothetical perspective, from the perspective of someone who somehow existed within it and could observe outward, the universe would not look like a place full of galaxies with some gaps between them. It would look like a place of profound darkness, punctuated at very large distances by faint threads of structure. The cosmic web, seen from inside a supervoid, would appear as a distant lattice, beautiful perhaps in the way that distant city lights are beautiful seen from a dark wilderness, but remote and growing more remote over time. This inversion of perspective, placing the observer inside the void rather than outside it, does something interesting to the standard picture of cosmic structure. It reveals that the picture we have built, the maps and models and visualizations of the cosmic web with its luminous filaments and its labeled voids, is a picture built from a very particular vantage point. A vantage point inside the structure, inside the web, inside a galaxy in a filament, in an overdense region that represents a small fraction of the total volume. The picture is accurate, but it is not neutral. It emphasizes the structure because the observers are inside the structure. A map of the universe drawn by an observer in the void, if such an observer could exist, would emphasize the emptiness because that is the majority condition of the observer's environment. There is no map of the universe drawn from inside the void. There will never be one, for reasons we've already established, but the thought experiment of imagining such a map is not idle. It is a way of asking, how much of our picture of the cosmos is a picture of the cosmos, and how much is a picture of where we happen to be in it? This is a question that cosmologists have grappled with under the technical label of the anthropic principle, the observation that the universe we observe must be compatible with the existence of observers, because if it weren't, there would be no observers to make the observation. In its weak form, this is almost trivially true, Of course, we find ourselves in a region of the universe where the conditions for our existence are met. We could not find ourselves anywhere else. But the weak anthropic principle, while logically valid, does not fully capture what the Boötes Void makes concrete. Because the void makes concrete not just the abstract possibility that some regions of the universe are inhospitable to observers, but the specific, measured reality that the majority of the universe's volume is already, presently, in a state where complex structure and observer-producing chemistry are essentially absent. We are not in a typical location. This is not a philosophical musing or a statement of cosmic humility. It is a quantitative claim supported by the data. The region of space we occupy inside a galaxy, inside a filament, in the 30 or 40% of the cosmic web's volume that is meaningfully overdense, is not representative of the universe's average conditions. The average conditions, weighted by volume, are conditions of emptiness, darkness, near absolute zero temperature, no stellar radiation, no chemistry, no gradients, no processes of the kind that produce complexity. The universe, as experienced by the beings who experience it, is radically unrepresentative of the universe as it actually is. And the Boötes Void is the starkest available illustration of this. Not because its unique voids are everywhere, but because it is the largest known void, and its size makes the contrast undeniable. 330 million light-years of almost nothing, sitting 700 million light-years from a small, rocky planet where beings have evolved the capacity to look outward and ask what is out there. The juxtaposition is not symmetrical. The planet is extraordinarily specific in its conditions. The void is extraordinarily general in its emptiness. And the fact that the specific conditions produced beings capable of finding the general emptiness is not a feature of the universe that the universe arranged intentionally. It is a consequence of the same gravitational dynamics that produced both the overdense regions and the voids. Gravity concentrated matter. Matter produced stars. Stars produced chemistry. Chemistry produced complexity. Complexity produced observers. Observers found the voids. The void did not wait for them. The void has no capacity to wait. But it was there, expanding slightly, year by year, across the 14 billion years it took for observers to appear somewhere in the cosmic web and point their telescopes in its direction. Now we reach the question that everything so far has been building toward. The question that the physics establishes the conditions for, but cannot itself answer. If you were in the void genuinely in it, floating in its center in a suit that could sustain you indefinitely, with no ship, no signal, no means of departure, what would the experience of time be like? Not time as measured by a clock, which would continue to tick at its normal rate, regardless of surroundings. Time as experienced, time as the felt sequence of events. Because the experience of time is not simply the measurement of duration, it is the registration of change. Psychologists and neuroscientists who study time perception have established, with considerable consistency, that the subjective experience of duration is closely tied to the amount of information processed during that duration. When a lot is happening, when stimuli are numerous and varied, when attention is engaged, when memory is being actively formed, time feels full, dense, richly textured. When very little is happening, when stimuli are absent or monotonous, when attention has nothing to grip, when memory formation slows because there is nothing distinct to encode time, feels thin, extended. In extreme cases, it stops feeling like time at all and becomes something more like an undifferentiated suspension. In the Boötes Void, with no light sources, no sounds, no temperature gradients, no objects to observe, no surfaces to touch, no gravity to orient against, the rate of information arriving from the external environment would approach, though never quite reach, zero. The only remaining sources of sensory input would be internal, the body's own processes, the heartbeat, the breath, the proprioceptive signals of the body's position and tension, the thoughts arising in a mind that has nothing external to think about. And the mind, as we established in the first part of this exploration, is not designed to run without external input. It generates its own, when deprived of the genuine article, hallucinations, false patterns, the projection of structure onto the blank screen of an empty environment. But there is something beyond the hallucinations that sensory deprivation research doesn't fully model, because sensory deprivation on Earth, however extreme, is not permanent. Subjects know, even when they can't feel the knowledge, that the outside world continues to exist, that the tank or the chamber has walls, that there are people outside, that the session will end. That darkness is temporary. The knowledge of bounded duration shapes the experience of sensory deprivation in ways that are difficult to fully isolate in experimental conditions, because you cannot ethically eliminate a subject's knowledge that they will eventually be released. In the void, that knowledge would not exist, not because you would forget it, but because it would eventually become untrue. In the void, with no means of departure, the duration is not bounded. It is open. And the open duration, the not knowing whether hours have passed or decades, whether your memory of Earth is minutes old or centuries old, whether your sense of being a continuous self persists or has fractured in ways you can no longer detect, is a different kind of experience than bounded deprivation. It is not worse in a simple way. It is different in a fundamental way. It is an experience for which human consciousness was not designed, in an environment that human existence never anticipated, for a duration that has no precedent in any life that has ever been lived. And here is the strange, quiet thing at the center of all of this. You would still be there. Whatever the void does to time perception, whatever it does to the sense of self and orientation and continuity, the physical fact of your presence in that volume would persist. You would be a small, warm, chemistry-driven system, maintaining improbable order in the middle of a region defined by the absence of order. The second law of thermodynamics would continue to apply entropy within your body, would continue to accumulate, processes would continue to run down. The biological machinery that sustains consciousness would continue to require energy and would eventually exhaust whatever reserves your suit carried. But until that exhaustion, you would represent something genuinely anomalous within the void, a point of complexity, a source of heat, a system maintaining internal gradients, temperature, chemical, electrical, of the kind that the void itself has none of. In a region of 330 million light-years of near maximum entropy, you would be a local exception, a small, temporary reversal of the void's dominant condition. Not because you had disrupted the void, your presence would be physically irrelevant at any scale larger than your immediate vicinity, but because you would be carrying, in your body and your mind, the conditions that the void lacks, the conditions that the cosmic web produces and that the void has evacuated. You would be, in the most literal sense, a representative of the universe's generative minority, briefly and improbably present in its inert majority. Whether that thought would comfort you, or whether comfort would be accessible at all in that environment, is a question that only the experience itself could answer. And the experience, by the logic of everything we've established, is one that no one has had and no one will have. The void remains unvisited, not for lack of curiosity, not for lack of imagination, but because the distances involved are not merely large. They are large in a way that renders them permanent for any technology that operates within the known physics. 700 million light-years is not a distance that more powerful engines will one day overcome. It is a distance measured in a fraction of the speed of light, sustained across a fraction of the age of the universe, and even that fraction is beyond any conceivable engineering. The void is not waiting to be explored. It is waiting in the only sense that a region with no capacity for waiting can wait to be left alone. And it will be, in the far future in timescales so remote that the sun will have long since exhausted its fuel, the Milky Way and Andromeda will have long since merged, the stars of the resulting galaxy will have long since burned out, and the stellar remnants, white dwarfs, neutron stars, black holes will have had time to slowly decay through processes so slow that their rates are measured in units larger than the current age of the universe. The Boötes Void will still be there, larger, more isolated. Its boundary galaxies long since receded beyond communicability. Its 60 interior galaxies long since dimmed to cold remnants of whatever they were. The void's temperature, barely above absolute zero now, fractionally lower than. The expansion of space continuing its work, slowly widening the distances that were already too vast to cross. The void will not notice. It has never noticed anything. It has no mechanism for noticing. But it will persist, and it will grow, and it will increasingly resemble the final state of the universe as a whole, that distant, theoretical equilibrium where nothing happens because there is no gradient left across which anything could happen. The void is not the end of the universe, but it is a region that has already begun to resemble the end, and the universe is, on its longest timescales, moving toward resembling the void. This is the thing that the numbers on the telescope data don't convey. The void is not simply a large, empty region that exists alongside the rest of the universe. It is a direction, a destination that the physics of the universe are navigating toward, in the way that a river navigates toward the sea, not intentionally, not with awareness, but as the inevitable expression of the forces that govern it. The cosmic web is not a stable structure. It is a transitional one. The dense filaments are dense because gravity has not yet finished its work of redistribution. The voids are empty because gravity has, in those regions, largely completed that work. The filaments are the universe in process. The voids are the universe approaching rest. And somewhere in that progression, somewhere in the transition from process to rest, from complexity to simplicity, from the improbable arrangements of matter that generate chemistry and life and observation to the probable arrangements that generate nothing, somewhere in that transition is the question that the Boötes Void poses, and that neither cosmology, nor philosophy, nor any other discipline has yet answered. The question of what it means that the universe produces, in a small fraction of its volume, and for what is almost certainly a small fraction of its duration, beings capable of looking at it and asking what it is. Beings who find, when they look carefully, that the majority of the universe is already past the point where such beings are possible, that the conditions for their existence are the exception, that the emptiness is the rule. The Boötes Void is not a warning. It has no communicative intent. It is not asking to be understood or urging any particular response. It is simply there, vast and dark and cold, and almost perfectly empty in the direction of a constellation that ancient Greek astronomers named for a herdsman for reasons that have nothing to do with the 330 million light-year absence that sits beyond it. It is there in the way that absolute things are there, not by accident, not by design, but as the consequence of physics operating consistently across time. The consequence of gravity pulling matter away from some regions so thoroughly that the regions themselves became defined by the pulling away. What exists in the void, in the end, is not nothing. It is the record of what used to be there, and the evidence of where it went, and the physical expression of a process that the entire universe is undergoing at different rates in different places. The void is full of history, empty of presence, but full of history. Every cubic light year of it is the consequence of 14 billion years of physics. The temperature is a consequence. The isolation is a consequence. The 60 lonely galaxies, slowly running down, are a consequence. And the fact that there is no one inside the void to register any of these consequences, no observer to process the darkness, no mind to feel the cold, no instrument to measure the silence, is itself a consequence of the same process that created the void, the process that separates matter into dense and empty, generative and inert, observed and unobservable. The universe, in the Boötes Void, has produced a region that cannot know itself, and in the cosmic web beyond it, in the galaxies and solar systems and planets and biospheres that gravity also produced, it has created beings who can know the void from outside but cannot enter it, cannot experience it, cannot fully close the gap between the description of emptiness and the reality of being inside it. That gap is not a failure of science. It is not a problem that better telescopes or faster computers or more precise models will eventually resolve. It is a structural feature of the relationship between observers and the universe. They inhabit a universe that is mostly not the kind of place where observers exist, observed by beings who are, themselves, a brief and local exception to the prevailing conditions of the cosmos. The Boötes Void will outlast everything that is currently alive. It will outlast the Sunday. It will outlast the stars. It will outlast, by inconceivable margins, the civilization that discovered it and the species that built the instruments to measure it. It will be there, larger, darker, colder, more complete in its emptiness, when there is nothing left in the filaments of the cosmic web that is capable of pointing in its direction and asking what it is. And then the question no one can answer is whether the universe at that point will still be a universe in any meaningful sense. Whether a cosmos with no remaining observers, no remaining complexity, no remaining gradients to drive any process of any kind is still the universe, or whether the concept of a universe requires, at its minimum, something in it capable of being a universe too, something that receives it, something that the 14 billion years of structure formation was, in some sense, building toward. That question does not have an answer yet. It may not be the kind of question that answers are possible for, but it is the question that the Boötes Void, more than any other structure in the observable cosmos, makes unavoidable. Because the void is what the universe looks like when it stops building toward anything. And the void is, by volume, what the universe mostly already is. The herdsman of Boötes stands in the northern sky, and in the direction of his constellation, 700 million light-years away, the universe has already shown us what it is becoming. We just haven't decided yet what to do with the knowing. And there is something beyond that, something in the structure of what the void implies about the nature of the structures that surround it that we haven't fully examined. A question about the dark matter that fills even the void's emptiness at levels too diffuse to detect directly. About the possibility that the void's apparent emptiness conceals dynamics that our current instruments cannot resolve. About whether the void's boundary, where the filaments give way to the expanding emptiness, marks a transition that is physically sharp or physically gradual in ways that matter enormously for our models of how structure forms and where it leads. About whether there might be, in the largest voids, phenomena that only become possible in environments that are this empty. Phenomena that the density of the cosmic web's active regions suppresses or obscures. Phenomena that require the absence of everything else in order to manifest. That possibility, the possibility that the void is not merely the absence of the cosmic web's contents, but the presence of something that the cosmic web's density prevents us from seeing, is where the next question begins. And it is a much darker question than the one we started with.